In August 2011, a wildfire had been burning underground in Virginia's Great Dismal Swamp for weeks when Hurricane Irene made landfall. The hurricane dumped 12 inches of rain directly onto 6,500 acres of active fire. The fire did not go out. It burned for 111 days total, smoldering beneath standing floodwater, consuming the soil from underneath, utterly unaffected by the largest rainstorm anyone could ask for. If 12 inches of hurricane rain cannot extinguish a fire, the fire is not on the surface. It is inside the earth. And once you understand why the ground itself was burning, why 9,000 years of accumulated soil had become fuel, a network of aluminum culverts and 6-inch boards, each costing less than $100,000, stops looking modest and starts looking like the only possible response. The Great Dismal Swamp is a peatland straddling the Virginia and North Carolina border. For most of its 9,000-year history, it was fireproof. Then, humans drained it. For 260 years. And the carbon that had been sealed in the ground since the Neolithic was suddenly open to the air. A healthy peatland works because of a single physical condition: the ground is permanently underwater. The Great Dismal Swamp sits on a low hillside roughly 6 meters above sea level. It has no major river feeding it. What it had, for millennia, was a geology that trapped rainwater at the surface. A layer of dense clay beneath the soil that prevented water from draining downward, combined with a gradient so flat that rainfall had almost nowhere to drain sideways. The result was continuous saturation. The soil consisted of more than 85% water by volume. In those conditions, waterlogged, oxygen-free, highly acidic, dead vegetation does not decompose. Leaves fall, roots die, woody debris accumulates, and none of it rots. Year after year, century after century, that undecomposed organic matter compressed into peat. In the deepest zones of the swamp, the peat layer reached 14 feet thick. Nearly 9,000 years of continuous carbon deposition locked permanently into the ground by water. The trees that grew in this saturated ground, Atlantic white cedar and bald cypress, were themselves part of the engineering. Their roots formed elevated mounds that created a texture of wet hollows and dry ridges across the swamp floor, stabilizing the surface and giving new seedlings a place to germinate above the standing water. The trees built the terrain. The terrain held the water. The water preserved the soil. The soil fed the trees. A closed loop running for 90 centuries without interruption. This peat was functionally fireproof. You cannot burn soil that is 85% water. You cannot oxidize carbon that has no access to oxygen. The chemistry was sealed. The drainage was initiated in 1763 by a land speculation company that included George Washington. A 22-mile canal was hand-carved through the peat by enslaved laborers, built to facilitate timber extraction and agricultural conversion. Over the next 2 centuries, that single canal expanded into more than 150 miles of drainage ditches and logging roads cut directly through the peat. Here's why that mattered. The ditches didn't just remove standing water from the surface. They created artificial low points, drainage gradients that the water table bled toward continuously, day after day, year after year. Across vast sections of the swamp, the water table dropped by several feet. And when the water left the peat, something else took its place. Oxygen. For the first time in 9,000 years, atmospheric oxygen penetrated the peat profile. The bacteria that had been suppressed by acidic, saturated conditions, organisms that require oxygen to function, suddenly had access to the largest reserve of organic carbon on the eastern coastal plain. The ground wasn't just drying out. It was being digested from within. The bacteria ate the peat. They metabolized solid organic carbon that had been accumulating since the end of the last ice age and converted it directly into carbon dioxide, an invisible, continuous off-gassing that has released an estimated 50 million metric tons of it since colonial-era drainage began. That was the slow bleed, measured in centuries. The immediate mechanical problem was what the consumption did to the structure of the soil. As bacteria worked through the organic matter and water continued draining from the pores, the ground physically collapsed. The peat shrank. Elevations dropped. And because the swamp sits on a sloped hillside rather than in a bowl, that collapse permanently altered the drainage gradients, making it harder. not easier, for water to pool back into the damaged areas. The land was subsiding toward a shape that made its own recovery less likely with every passing year. That subsidence exposed deeper peat to drying, and when peat dries past a certain threshold, its chemistry shifts permanently. The dried soil becomes water repellent. Instead of absorbing rainfall like a sponge, it seals over and sheds water off its surface. This is the property that would later defeat Hurricane Irene, and it is the physical reason that every conventional firefighting method was doomed before anyone arrived on scene. The biology compounded all of it. The native Atlantic white cedar and bald cypress, trees that require saturated roots, died off across large areas of the swamp. They were replaced by red maples, a dry adapted hardwood that functions as a biological pump. Red maples pull whatever remaining moisture exists in the soil and vent it into the atmosphere through their leaves at far higher rates than cedar ever did. The replacement species was actively accelerating the very drying that killed the species it replaced. The drier the peat got, the more it oxidized. The more it oxidized, the more the ground collapsed. The more the ground collapsed, the harder it became to re-wet. The harder it was to re-wet, the more the maples pumped out whatever remained. Every year without intervention made the next year's recovery less likely. In 2008, a spark from logging equipment ignited the South One fire. Hundreds of firefighters deployed conventional tactics, bulldozed fire lines, aircraft water drops, miles of surface hoses. The fire dropped below the ground and burned through the peat itself, smoldering at low temperature, spreading through root systems horizontally and vertically, completely insulated from anything happening above. It burned for 121 consecutive days. It cost $11 million to suppress. It became the longest continuous wildfire in Virginia's recorded history, and for a while the assumption was that 2008 represented the worst case. 3 years later, on August 4, 2011, lightning struck the 2008 burn scar. The vegetation that had regrown on the damaged peat was mostly tall grass and invasive reeds, dense, volatile surface fuel sitting on top of peat that was drier than it had been before the first fire consumed part of it. The lateral west fire ignited and immediately entrenched itself underground. It burned for 111 days across 6,500 acres. Late in August, Hurricane Irene arrived. 12 inches of rain. The surface flames went out. The underground fire continued as if nothing had happened. The water pooled on top of the sealed water-repellent crust and never reached the smoldering front burning 3 to 4 feet below. Mature trees whose root systems had been consumed from underneath toppled into the smoldering ground. Fresh fuel. The cycle continued. If the largest rainstorm imaginable cannot extinguish this fire, the problem is not insufficient water. The problem is that water from above cannot reach combustion happening below a sealed barrier. Every conventional method, aerial drops, surface hoses, a Category 1 hurricane, operates on the same assumption. Water falls from above, meets fire, fire goes out. In degraded peat, that assumption is inverted. The fire is underneath the barrier. The water sits on top. The logic ran backwards. If water from above cannot reach a fire burning below a sealed surface, the water has to come from underneath. During the lateral west fire, after Hurricane Irene failed and months of conventional suppression had accomplished nothing, engineers abandoned surface tactics entirely. They brought in industrial, cruciform agricultural pumps, massive impellers powered by tractor engines, each moving roughly 18,000 liters per minute, and ran them in reverse. The fire was burning at a higher elevation than the available water in distant lakes and uncompromised canals. Gravity would not deliver the water. So the pumps forced it backward, upstream against the natural gradient of the canal system. Temporary dams went up across the Corapeak Ditch and adjacent canals every 1 to 2 kilometers. The sealed ditches flooded. And because those ditches were cut directly into porous peat, the pressure of all that backed up water had nowhere to go but sideways, through the ditch walls, into the surrounding soil. The water pushed outward and upward into the burning peat from below, raising the water table directly underneath the fire. Instead of trying to force water down through a surface that repelled it, they pushed water up through material that accepted it. The smoldering root systems were submerged from underneath. The fire drowned. That improvised hack during a crisis became the blueprint for a permanent system. Since 2012, hydrologists from the United States Fish and Wildlife Service and the United States Geological Survey have installed 75 adjustable water control structures across the swamp's 150-mile ditch network. Each one costs between $50,000 and $100,000, deliberately low-tech. A corrugated aluminum culvert, roughly 2 meters in diameter and up to 14 meters long, sits in the bed of a drainage ditch beneath an existing spoil pile road. At the upstream end, a vertical riser with grooved channels. Into those channels, hydrologists stack removable 6-inch aluminum or wooden boards, stop logs, to raise or lower the water level. When the boards go in, the ditch backs up. The swamp is almost perfectly flat, so the water doesn't just fill the canal, the pressure forces it laterally through the porous ditch walls and into the surrounding peat, resaturating the soil from the inside out. A single structure controls the water table across hundreds of acres of dense forest. The system is adjustable for a reason. Ahead of hurricanes and tropical storms, refuge staff pull the boards to drain the canals rapidly. The empty ditches and adjacent peat become a massive sponge that absorbs incoming rainfall, protecting downstream cities like Chesapeake and Suffolk from flooding. On coastal-facing canals, one-way flex valves allow fresh water to drain out but snap shut against incoming saltwater during storm surges. The entire network functions as a landscape-scale valve system, tuned manually to the weather. But fire prevention was only half the equation. Peat is not just soil. It is stored carbon. Atmospheric carbon pulled from the air by vegetation, dropped to the forest floor, and locked into the ground by saturated, oxygen-free conditions, layer by layer, for 9,000 years. Draining the swamp reversed the direction of that carbon flow. The soil switched from absorbing carbon to emitting it. 50 million metric tons of carbon dioxide released since colonial drainage began. The two fires alone, South 1 and Lateral West, vaporized peat so thoroughly that the ground dropped by up to 4.5 feet in places. The carbon consumed in those two events will take approximately 1,740 years to reaccumulate at the peat's natural deposition rate. Reflooding this swamp is not just fire prevention, it is plugging a hole in the planet's carbon budget. The restored sections now actively sequester 200,000 metric tons of carbon per year, equivalent to taking 42,000 cars off the road annually. The proof arrived in 2022, delivered by a storm no one designed as an experiment. At Pocosin Lakes National Wildlife Refuge in North Carolina, a sister peatland using the identical water control structures and rewetting approach, a severe electrical storm passed overhead. 4 separate lightning bolts struck directly onto rewetted refuge land. The saturated peat absorbed the strikes without igniting. Not a single fire. A 5th bolt from the same storm hit privately owned farmland 1.5 miles away, where the peat was still drained by agricultural ditches. The dry peat ignited immediately. An uncontrolled underground fire burned nearly 2,000 acres and required 10 days of continuous suppression. Same storm, same lightning, same soil. The only difference was whether an aluminum culvert and a stack of 6-inch boards had raised the water table. Across the managed zones of the Great Dismal Swamp, water tables have risen by half a foot to a full foot. The catastrophic ground subsidence has stopped. In 2019, 2 separate wildfires ignited within the refuge, and both were rapidly contained with minimal damage, a result that would have been unthinkable a decade earlier. Over 73,000 Atlantic white cedar seedlings have been planted across 123 acres of burn scar, and in zones where soil moisture stays high, natural cedar regeneration has reached densities exceeding 14,000 stems per hectare. The native trees are reclaiming ground that invasive red maples held for decades. To give you a sense of the economics, the entire 75-structure water control network cost between $3.75 million and $7.5 million to install. The suppression of the 2008 South 1 fire alone, one fire, one event, cost $11 million. And that fire still burned for 121 days and released hundreds of thousands of tons of ancient carbon. Economic modeling projects, the current management approach, generates $326 million in net societal benefits through avoided emissions, prevented fires, and reduced healthcare costs. Preventing a single catastrophic peat fire saves $3.69 million in emergency room visits from smoke inhalation in the surrounding cities. 75 aluminum culverts. A few hundred 6-inch boards. That is the infrastructure currently holding a 9,000-year-old carbon vault together. But the swamp is being saved. It is not yet saved. The current network is insufficient for full hydrological recovery. Monitoring data shows that while subsidence has been arrested, new peat accumulation has not yet restarted. The fire damage from 2008 and 2011, a full meter of peat burned away in the worst areas, cannot be undone quickly. Degraded peat permanently loses some of its original capacity to hold water, making it harder to keep wet than undisturbed peat ever was. And there is a deeper structural tension. To truly restore the pre-1763 hydrology, the entire 150-mile ditch network would need to be backfilled and the miles of elevated spoil pile roads demolished. Those roads are the same roads that refuge staff drive every week to reach the water control structures, adjust the stop logs, and respond to fire emergencies. The infrastructure that caused the damage is the same infrastructure required to administer the ongoing treatment. Hundreds of miles of legacy roads and spoil piles still block the natural sheet flow of water across the swamp. The system keeping this landscape alive depends entirely on a small team of hydrologists manually adjusting aluminum boards season by season, storm by storm, guided by groundwater models and weather forecasts. The Great Dismal Swamp broke along a specific mechanical chain. Drainage introduced oxygen. Oxygen triggered consumption of the soil. Consumption caused the ground to collapse and seal over, and that seal trapped fire beneath the water. Every conventional response, hoses, aircraft, a hurricane, failed because they operated on the wrong assumption that water falling from above would reach a fire burning below. The fix reversed the direction. Water pushed sideways, pressure from below. The system that destroyed a 9,000-year-old carbon vault was a network of hand-dug ditches. The system rebuilding it is a network of aluminum culverts. Neither required advanced technology. Both work on the same physics. The only thing that changed was which way the water flows.